Okay, I'm going to just go through and work through some more examples. First example, a large tank initially contains 500 liters of fresh water. Brine is pumped in at a concentration of 0.1 kilograms per liter, that's an L, at a rate of 30 liters per hour. The well mix solution is pumped out at a rate of 20 liters per hour. So what do we have? We initially have 500 liters, and this word fresh water means there's no salt in the tank. So we're pumping in brine. So we've got that concentration at this rate, and then we pump it out at that rate. So this is in, this is out. So we've gone through here, read this carefully, figured out what's important. So that was the first step. So let's organize what we have. So we've got this tank. The initial volume is 500 liters. And we are pumping in brine with a concentration of 0.1 kilograms per liters at 30 liters per hour. And we're pumping out at a rate of 20 liters per hour. All right, so what do we have? We have the volume at any time, and we're going to have some amount of salt at any given time. Okay. Actually, notice there's no question actually asked here. Let's ask, what is the concentration at any time? And notice the concentration is going to be the amount of salt divided by the volume. Okay. So, all right. So we've figured out the situation. We've defined our variables, and T is in hours. All right. So now, what are we going to do? Let's see. So the physical principle is the rate of change of the amount of salt. All right. So this is A is in kilograms. So the derivative is going to be kilograms per hour, is the rate that stuff comes in minus the rate that stuff goes out. And these rates, again, are in kilograms per hour. All right, so rate N. For the rate N, stuff is coming in at 30 liters per hour. And again, I want kilograms per hour. I've got the per hours there. I need to get rid of liters and I need kilograms. But notice, if I multiply by the concentration, that's kilograms per liters. Liters cancel. I'm left with kilograms per hour, so that's 3 kilograms per hour. And notice this is concentration times flow rate. So that's going to help us for the next part. For the rate out, let's see, we have stuff flowing out at 20 liters per hour. And the concentration in this case depends on, is the amount divided by the volume. So I have A of T kilograms. So now I've got liters, kilograms per hours. I need to get rid of liters. So I'm going to divide by the volume, which is liters. So this gives me 20A over V of T. So I got to figure out my V of T. Well, for my V of T, the rate of change of the volume, again, is going to be rate in minus rate out. So the volume is liters, and so the rate of change is going to be liters per hours. So I have 30 liters per hour coming in, minus 20 liters per hour going out. So I have, 30 minus 20 is 10 liters per hour. So the derivative of V is 10. And I know that initially there's 500 liters. So now I've got my differential equation here and my differential equation here, and I'm missing so far the initial condition for A. But because it's fresh water, I know that initially there is 0 kilograms of salt in the tank. All right, so what do we have? We have dA dt is the rate in, which you said is 3 kilograms per hour, minus the rate out, which is 20A over V of t. A of 0 is 0. And the derivative of the volume is 10 liters per hour. And V of 0 is 500. All right, so my plan is I'm going to determine my V of t using V prime equals 10. That's going to be the easiest thing. I'm going to plug that into my differential equation for the A. I'm going to solve for A. Now notice when I solve this, I'm going to have a function of time. So this is going to have a function of time here, and it's not going to be separable. So I'm going to, most likely, this may not be the case, but most likely I'm going to have to use an integrating factor. And if that's the case, that's so much. Not much I can do about it. All right, so V prime is 10. So if I integrate both sides, the antiderivative of V prime is V. Antiderivative of 10 is 10t, but because I'm taking antiderivatives of both sides, I'm going to have a constant. I know that when I plug in t equals 0, that V of 0 we said is 500. 10 times 0 is 0, so C is 500. So V of t is 10t plus 500. All right, so that means my differential equation for dA dt is going to be 3 minus 20 divided by V of t, which is 10t. That's a 10t plus 500 times A, and A of 0 is 0. All right. Let's rewrite that and figure out what we're going to do here. So dA dt is 3 minus 20 over 10t plus 500 A. A of 0 is 0. Okay, again, it's not separable, right? My t's and a's are all combined, so I'm going to have to write this in a way which is going to allow me to use an integrating factor. Right, and the idea behind the integrating factor is that's my P of t. So that means R prime of t is whatever that is. I'm going to integrate that to figure out R. Take e to the r, multiply both sides, and if I've done everything right, the left-hand side is going to look like, let me rewrite that, the derivative of A times R e to the r. All right, if that doesn't work, I did something wrong. So R prime is 20 over 10t plus 500. I'm going to take the antiderivative of both sides. Antiderivative of the derivative is just R of t. And keep in mind I'm going to have a constant of integration when I'm done here. So what is this? Let's try U substitution. Let's get rid of this nonsense. So this is going to be 10 dt. Well, I've got a 20 dt, so I can write that as 2 over 10t plus 500 times 10 dt. There's my du, and there's my u. So this is the integral of 2 divided by u du, and that's 2 log of u plus c. All right. So again, my differential equation was 3 minus 20 over 10t plus 500a. A of 0 was 0. My r prime of t was 20 over 10t plus 500. My r of t we decided was 2 log of u plus c, where u was 10t plus 500. So r of t is 2 log of 10t plus 500 plus c. So my integrating factor is e to the r. It's going to be e to the 2 log of 10t plus 500 plus c. Can bring that 2 up. So in the inside, I've got 10t plus 500 squared plus c. I can break the plus into 2 parts. So that's e raised to the log of 10t plus 500 squared times e to the c. C is a constant, so e to the c is a constant. So let's just call the whole thing k. E to the log of anything is just whatever the thing is. So that's 10t plus 500 squared times k. All right. So let's multiply everything through. So I'm going to take this thing and multiply it through here. Oops, I gotta be careful. I'm gonna add this to both sides. So that r came from adding this term to both sides. I'm gonna multiply everything by my integrating factor. So dA dt times this. Oops, k times 10t plus 500 squared dA dt plus 20 over 10t plus 500 times 10t plus 500 squared times k times a all equals 3. So let's clean this up. Oops, I got to multiply the right-hand side by my integrating factor as well. Again, I got to multiply everything. Notice there's a k there, and a k there. I can just cancel that. And I've got a 10t plus 500 squared divided by 10t plus 500. So one of those cancels and I'm left with a 1. So what does that look like? I'm going to have 10t plus 500 squared times dA dt. And this is going to be 20 times 10t plus 500. Oops, that's just times a equals 3 times 10t plus 500 squared. Whew. All right, so that's a mess. Let me rewrite that. So my current differential equation now looks like 10t plus 500 squared dA dt plus 20 times 10t plus 500 a equals 3 times 10t plus 500 squared. All right, and if I did everything right, the derivative of that should be that, and that is indeed the case. The derivative of something squared, I'm going to take the 2 out, times the 10t plus 500, times the derivative of the inside gives me my 20 times that. So the left-hand side, by the product rules, the derivative of 10t plus 500 squared times a of t equals whatever was left on the right-hand side. So now if I take the antiderivative of both sides, antiderivative of the derivative just gives me the thing on the inside. So that's the 10t plus 500 squared times a of t. The antiderivative of this is going to be what? 3. So I'm going to have 10t plus 500 cubed over 3, but then I got to deal with that 10. That's going to be a 1/10 plus c. And I want to isolate that. So if I divide both sides by 10t plus 500 squared, so the 3's cancel. I'm going to have 10t plus 500 cubed divided by 10t plus 500 squared, times 1/10, plus c divided by 10t plus 500 squared. All right. Let me clean that up. So this is going to be 1/10 from here. All these cancel except for 1. And then this, nothing changes. All right. Okay. And now we know that initially, what did we have initially? Was a of 0 was 0. All right, if I go back to here. So I know we had fresh water in there originally. So if I plug in t equals 0, so everywhere I see a t, I replace it with 0. A of 0 is 0. 10 times 0, so I'm left with 500 there. And in there I'm left with 500 squared. And my goal is to find the c. So this is 50. I subtract 50 from both sides. So c is minus 50 times 500 squared. So my a of t becomes, so coming back to here, here, 1/10 10t plus 500 minus 50 times 500 squared over 10t plus 500 quantity squared. I'm not quite done though. Question I decided was going to be, what's the concentration? The concentration is going to be the amount divided by the volume. And we decided that the volume was, looking back, sorry, I'm going to go back and check my work. The volume was 10t plus 500. Basically, I have to divide everything by 10t plus 500. So the concentration is the amount in the tank divided by the volume. And the volume was 10t plus 500. And the amount in the tank was 1/10 of 10t plus 500 minus 50 over 500 squared over 10t plus 500 squared. So multiplying that through, I'm going to get, those cancel, so I get 1/10 minus 50 times 500 squared. This is 10t plus 500 cubed. All right. That was a mess. So the key thing, this is why you got to be really structured and very careful, because there's a lot of stuff going on here and it takes a long time and there's a lot of stuff to keep track of. Okay, next topic is something called Newton's rate of cooling. And for Newton's rate of cooling, the idea is this: the rate of change of an object's temperature is proportional to the difference between the object and the temperature of its surroundings. So the idea is you've got some object and temperature is going to change. It's going to want to reach equilibrium with the outside temperature. And so the idea behind Newton's rate of cooling here is we're looking at the rate of change of the object's temperature and the difference between the object's temperature and its surroundings. And so that's the surroundings are going to be called the ambient temperature. So we have the derivative of the temperature. That notation is pretty horrible. This is the temperature at time. So big T is temperature, small t is time. And then we have the difference between the object and the temperature of its surroundings. That should be the object's temperature. That's T minus the ambient temperature. And we're going to abbreviate this as T minus T naught. And for us, for now, we're going to just let that be a constant and see what happens. And so since these two things are proportional to one another, that means there's some constant. We'll call it K. So the derivative of the temperature, and this is derivative with respect to time, is equal to K times the temperature minus the ambient temperature. Okay. So let's look at an example. All right, so we've got a cup of tea, so this is the object. When we find it, its temperature is 70 degrees. We wait 30 minutes, and this temperature is 65 degrees Celsius. The ambient temperature, the outside temperature, is 18 degrees Celsius. So we assume that this mug of tea is going to want to get to 18 degrees Celsius. And we know that initially its temperature was 85 Celsius. And so now the question is, when, so we're looking for time, was the cup of tea poured? Okay. All right, so we've gone through, we've read things, we've got to organize. What do we know? We know that capital T is going to be the temperature at time t, and we are working in minutes for our temperatures, and for time is in minutes and the temperature is in Celsius. All right, and we know that T initial is 85. We know that when we found it, it was 70 degrees Celsius, and after we waited 30 minutes, it was 65 degrees Celsius. And the question is, what was the found time? At what time did we find it? And we can think of this as the time, how many minutes we found it after it was poured. All right, so now this is Newton's law of cooling. So this was a step one. So the rate of change of the temperature is going to be the temperature minus the ambient temperature, which is 18, but it's proportional to this, so this is times some constant k. And we don't know what k is, we just know it's some constant. And so what are we going to do? We're going to solve the dE. It looks like it's separable. We could use an integrating factor, but because there's no time in here, treating it as separable is probably going to be easier. So I'm going to try that. We will have k, we'll have an integration constant, and we don't know f. So once we solve it, we're going to use these three equations. So we've got three unknowns, three equations. And keep in mind, we do not care what k is, and we do not care what this constant of integration is. All we care about is that. So when we get there, and if we find a way to shortcut it or just ignore the k and c, we're going to go for the kill and just find f, because that's the only thing we need in this particular question. All right, so let's do it. So I have the derivative with respect to time of the temperature is k times t minus 18. I'm going to divide both sides by that because it's separable. Now I'm going to take the antiderivative of both sides. All right, so let's see, what do we have? We have the antiderivative of 1 over t minus 18 times the derivative. dt is k dt. K is a constant. The antiderivative of 1 over this, so I can think of this as because it's a dt, I can just think of this as the antiderivative of 1 over t minus 18 is log of t minus 18. This is a constant. This is kt, but because I took an antiderivative, I'm off by a constant between those two things. Oh, let's see. And again, let's do this. Let's isolate t and see what happens. So if I take the exponential of both sides, I get that. E to the log of anything is just the anything. But this is e to the something plus something. So I can take the first thing times e to the c. And look at that. C is a constant, so e to the c is a constant. So no, I've used k. Let's call this, let's just call it b, for lack of anything else. But b is a constant. That's all that matters. So t minus 18 equals b e to the kt. Oh, let's see. I know that t of 0 was 85, t of f was 70, and t of f plus 30 was 65, and this is all degrees Celsius. All right, I'm just going to plug these things in and see what I get. So if I plug in this first equation, t of 0 minus 18 equals b e to the k times 0. So I get 85 minus 18 is equal to b. Okay, so I immediately get b. b is 85 minus 18. So that's what, 75? So that's going to be, what, 67? 67. Okay. So my equation now looks like t minus 18 equals 67 e to the kt. All right, I'm just going to plug in this and see what it looks like, because I don't know. When t equals f, I get t of f minus 18 equals 67 e to the kf. Again, I don't know k and I don't know f. But I do know that when t is f, I'm going to have 70 minus 18. So what that's going to be is, what, 6052? Is that correct? Yeah. So that's 52 equals 67 e to the kf. And when I plug in f plus 30, so everywhere I see a t, I'm going to plug in f plus 30. So I can be careful, I'm using this equation. So it's e to the k f plus 30. T at f plus 30 is going to be 65. That's going to be kf plus 30k. Let me rewrite all that. So I have 65 minus 18 is 67 e to the kf plus 30k. Well, I can write that as two parts. So let's see. 65 minus 18 is going to be what? 55. 48. Is that correct? No. 47. 67. This is e to the kf times e to the 30k. What was my other equation? My other equation was 52 equals 67 e to the kf. So I have two equations, two unknowns. I only care about f. I don't see any shortcuts here. All right, I am going to use, so I know that 67 e to the kf is 52, so I'm going to plug that into here, use that to get k, then use this equation to find f. So because 67 e to the kf is 52, and I know that 47 equals 67 e to the kf times e to the 30k. I can replace that with 52. So 47 equals 52 e to the 30k. Divide both sides by 52. Take the log of both sides. The log of e to the 30k is 30k. So k is 1/30 log 47 over 52. So now, coming back to this equation, I can plug that in for k, and then the only thing left will be f. So I have 52 equals 67 e to the kf. So k is 1/30 log of 47 over 52 times f. Let me divide the 52 by both sides. So this becomes f over 30 log of 47 over 52. So I'm going to take the log of both sides. So this is log of e, f divided by 30, log of 47 divided by 52. Log of e to the anything is just the anything. So I'm going to have f divided by 30 times log of 47 over 52. And again, my goal is to find f. So I'm going to multiply by 30 and divide by that log term. So let's see. I just had log of 52 over 67 equals f over 30 log of 47 divided by 52. So f is going to be 30 log of 52 over 67 divided by log 47 over 52. Okay, and according to my notes, this is approximately 70.2 minutes. All right.